All right, I got my first good question here from Modern Physics, or at least first one making a video instead of just answering an email question. But this is from chapter 39, number 17. And this is about a Doppler shift. And I guess I will start by saying I guess I would understand why there's a question on this. I don't believe in the lecture videos I dealt with the Doppler shift. So let me point to the book where it's discussed and some other things. But also then in fairness of it, and this is what I want to do is I want to go through those lecture videos to see which topics were covered and which ones weren't, because we always kind of run out of time at the end of the semester and we don't always cover the same thing. So I don't believe this one is there, and therefore it will not be on the coming half test for modern physics. To try to be fair to you, the topics that will be covered on the test will be the ones that I actually got a chance to cover in those lecture videos. So I believe those are from the 2014 year. So anyways, whatever I covered that year is what we will call covered this year, given the circumstances. All right, so on with the problem. So the problem is about a Doppler shifting. And let me just kind of grab the book here, because there is, here's the book, and looking on page 1129, at least on the hard copy version of it, and I would be the same thing on the PDF, or at least not on the digital one, but you have to go a few more pages because the digital one, lists the number of pages. Anyway, so probably a little bit higher than this if you're on the PDF version. You will find this section, in fact, maybe I should flip. It is a subsection of section, time dilation, looks like section 4. Where it says here some of the consequences. And they talk about simultaneity, relativity of time, time dilation, length contraction. And I know I talked all about those on the videos, even some way to represent it with a space-time graph. And I talked a little bit about that on the video lecture, I'm pretty sure. But not this, the Doppler effect. So this is the equation I'm gonna start with. You can go back to our chapter, I believe it's 17, could be 18, where we did sound waves, and we did a Doppler effect. And you'll see this same overall equation with time dilation added to it. So it is a little different here, but than the sound one, but not much. And so if I copy that equation down, it says the observed frequency because of motion is equal to the, what I'll call the real frequency. I'll put an S here for the source. And then times, and it looks like we've got the square root of 1 plus V over C, and then over the square root of 1 minus V over C, where V is the velocity between the two objects, and C is the speed of the light. So again, if you had something, two things coming together versus going apart, but coming together, you would perceive then a higher frequency. So we'd call that a blue shift, because blue is the higher frequencies. And then if something was moving away from each other, we call that a red shift, because the frequency that would be perceived by the observer would be slightly lower in frequency, and that's towards the red. We don't necessarily mean it's actually red, but it's red shifted. Anyways, and so this one is actually red shifted, this problem anyways. But there's the equation, and it says then, make an approximation, that is, if the source is not moving that close to the speed of light, then we can simplify this equation. So let's simplify it, and I guess I'll begin by writing the frequency of the source. Let's write this as 1 plus V over C to the 1/2 power. And let's write this one in the denominator as 1 minus VC to the negative 1/2 power. So everything's in the numerator there. And so here's the frequency of the source. And let's take a look at this one. And here's what they mean by simplify it. Let me grab the book again. We had done this earlier in the semester. And I think we did it on the lecture videos for the kinetic energy. But we can expand this in a binomial expansion. And so looking at Appendix B here, looks like B.5, series expansions. Move that over to here. So series expansions. And then over to here, looks like it's page A13 in the appendices, which got a lot of math in it. But here it says, if x is much smaller than 1, you can use this generalized equation. And by the way, here is the sign. In fact, here is the full expansion up here. But here is what we can do if x is small. And because, you know, cube. And I guess I shouldn't get focused on the small angle approximation for the sine. But now we're going to do and you can run through this if you want, a Taylor series. And this is 1 plus nx. And if we did the next term, it would be n times n minus 1 x squared over 2 factorial, and so forth and so on. But again, those are all higher powers of x's. So if x is small, you start raising it to higher power, it's really, really, really small. And so we can ignore that. And so I'm going to take advantage of this binomial expansion here. And so keep that in mind here. And so let me move the book out of the way and put my piece of paper here and then say, all right, if I have this plus thus, and remember, this is small. So if we're talking about speeds that are small compared to the speed of light, and speed of light is huge, and so maybe we'll just call this 10%. That's what we did for the kinetic energy expansion. So if we're under 10% the speed of light, which is really, really fast, but if we're under 10% the speed of light, then we can replace this with 1 plus, and if you remember, maybe I should write it here, it said 1 plus x to the n would be 1 plus nx is what they wrote, and of course this pattern continues because it's a well, binomial expansion, or I'll just do a Taylor series, and then this is the derivative each time, and the derivative keeps getting higher and higher. But ignoring those, the power that it's raised to is 1/2, so I'll put a half, and the x here is the v over c. And I'll just indicate other terms, but that'll be enough to solve the problem. And then likewise here, so this would be 1, and this one is kind of interesting. We might want to think of this as 1 plus a negative v over c, so it looks like this. So we'd have 1 plus, and the n would be a negative 1/2, and the x would be a negative v over c. And of course, there'd be higher order terms, which again, I'll just ignore here. And of course, if you look at that, the negative and the negative cancel off, and these two are the same thing. And so we could write this as 1 plus, and they'll have a 1/2 v over c. And I'll just put a square here, since these would be the same thing, and if I ignore higher order terms. And then squaring a binomial will be 1 plus, and this would be like a plus b squared. So there's the a squared. Then it's 2 times a times b, and then times b squared. But again, if we're willing to drop off higher orders, because those v over c is kind of small, let's just say 1/10, and you square it over here to 1/100th, we can say the same thing here. We're squaring it, so we can kind of factor that off. So again, instead of using the exact equation, we might come up with an equation that is pretty close to being true if you are small compared to the speed of light. And so taking, again, small compared to the speed of light, that's a 10th, then the 1/100th, we'll just, don't worry about that. So this says that it's the frequency, and then it's 1 plus this, let's see, 2 cancels here, and I get my V over C. So there's my observed frequency. Now, with that in mind, I guess I should continue here. Okay, now that then is the simplification of that. Okay, so now, since this problem has to do with wavelength, we've got to change from the frequency to the wavelength. So I'll just put that the speed of light, c, is equal to wavelength times frequency. And that can be what I'll call the real wavelength times the real frequency, so let's call those the sources. But it would also be true for the observed wavelength and the observed frequency. And so that's what I have here. And so if we kind of come over here and ask, okay, what is our then observed wavelength? Then I would have, I guess, something that looks like this. I would have the wavelength of the source times the frequency of the source divided by the observed frequency. And the observed frequency is what we just did up here. So this would be the wavelength of the source and the frequency of the source. And so let me put up here the frequency of the source and 1 plus V over C. Okay. Now, of course, this would cancel off. And, of course, you can then take this and write it, wavelength of the source, and write it as 1 plus V over C to the negative 1. Again, if you are talking about small speeds compared to the speed of light, we can do this same binomial expansion up here. So this would be 1 plus, and this time it's raised, so my n is a negative 1, and my x is the V over C, and the higher order terms we ignore. And so this is saying the observed wavelength would be the real wavelength times 1 minus V over C. And I suppose, by the way, I should point out that I'm solving this from this equation in the book, which, if you remember way back when we did Doppler effect, we called V positive when they were coming together. And so negative when they are moving apart. I say that because we can write this then as the wavelength of the source minus then the wavelength of the source of V over C, and then this is the wavelength of the observer. And if we then do something such as this, that we say, okay, what wavelength does the observer see compared to what the real source is? We have a negative wavelength of the source, V over C here. And the reason I point that out is because this right here would be the change in the wavelength. And as I look at the solution, it looks like they've used the V the other way around. They've given it a positive as it moves out. So my equation up here had a positive and a negative down there. And as I glance over at the solutions, I see that it's slightly different because they define V a little bit different. So again, in mine, notice that I am using the V as defined in the book, and so together it is positive. So as I spread out, it is negative, and so this is going to have a negative number here, and so there's going to be a bigger wavelength. The change in wavelength can be a positive a number. Now, I'll keep going with this. I think I can squeeze it into here because then delta lambda over lambda, this would be the lambda of the source. So when I divide this here, I would have a negative than this V over C. And that's what I think we were asked. Let me look back at the question, yeah. And so we were asked to show that the change in wavelength compared to its wavelength, so you would call the fractional change in wavelength, is equal to the fractional of the speed compared to the speed of light. And so we've got this fraction compared to the fraction. And so the fractional change of the wavelength is related to the fractional of the speed. And again, just be careful with your sign there, because again, if things are moving apart, I would put a negative velocity there. Whereas I think in the solution manual, they're going to call that a positive. In fact, actually in the problem there, they do that. So maybe I'll just say, you know, absolute value makes then a positive. And then it'll look more like the solution to part A. Okay, well then part B is just plug some numbers in here. And so it already tells us right away that this phenomenon is red-shifted. And so red-shifted would tell me it's moving away. So if I start with, you know, delta lambda over lambda, and I'll use the negative sign here, but they tell us in the problem that it is red-shifted by 20 nanometers for light, and if I remember this number right, this looks like the violet light coming from a hydrogen atom. So as they study the distant galaxy, they're looking for a specific kind of wavelength, a specific kind of light coming from hydrogen, which always makes a good choice because there's mostly hydrogen out there. And then, of course, I would have this negative V over C. And then, so to get the velocity, we would have, and in my notation, I'd have a negative. But grabbing my calculator here, we've got a shift of 20 parts out of 397. And so that would be 0.05. I noticed they go a little bit further, so I'll go to 0.0504 C. And so there would be the velocity there. All right.